I'm and I welcome you to my lecture series on computer and network security. In this video, I will discuss one of the most important applications of cryptographic hash functions, namely message authentication. And before we go into more details about message authentication, let's refresh our memory about the types of attacks that can be performed against message transmissions, for example over a network such as the internet. The first one is disclosure of message content, where an attacker is able to read the content of a private message. The second one is traffic analysis, where the attacker is not able to read the contents but is able to derive some information about the communication, such as the frequency, type of application, and so on. These two types of attacks are countered, they are passive attacks, and are countered using confidentiality mechanisms, such as symmetric encryption. Third type of attack is a masquerade attack. In this type of attack, an attacker will pretend to be someone else in order to participate in a communication to which he doesn't have the right to participate. Fourth one is content modification, where the contents of the message is changed. Fifth one is sequence modification, where the content of the message remains the same, but the order in which they are received can be changed. In a timing modification, messages can be delayed or replayed. These four types of attacks can be countered using message authentication. Finally, there is source repudiation and destination repudiation, where, respectively, the source or the destination cannot deny having taken part in the communication. Message authentication does not help against those types of attacks. However, digital signatures can help against source repudiation. And from the previous, it is clear that there's a lot of overlap between message authentication and digital signatures, as they help protect against very similar types of attacks. So let's define both concepts here formally. Message authentication is the verification that the received message has not been altered. This means it hasn't been modified, no new information has been inserted, no information has been deleted, or it is not replayed. On the other hand, a digital signature is a message authentication technique that also includes measures to counter source repudiation. So to ensure that when someone sends a message, the receiver can always verify that that person indeed sent a message and they cannot deny it afterwards. And a message authentication function is a function that produces some sort of authenticator to authenticate a message. And there are three main classes of message authentication functions. The first one is a hash function, which create a fixed length hash value to serve as the authenticator. The second one is encryption. If we encrypt a message, the ciphertext can serve as the authenticator. However, this is a heavyweight version of authentication, as usually encrypting a message is more computationally complex than creating a hash value. The third one is a message authentication code, or a MAC. This is a fixed length value resulting from the message and a secret key, and this fixed length value serves as the authenticator. And let's take a closer look at how these three types of message authentication functions work. And we'll start with hash functions. I already briefly explained how hash functions can be used for message authentication when talking about the length extension attack. So this kinds of message authentication can be vulnerable to this type of attack. How does it work in detail? We take our message M, we concatenate it with a shared secret key that is shared between the sender and the receiver, and take a hash value of this combination. Why do we need to combine the message with some shared secret key? Well, if we would just hash the message without a key, anyone could intercept the message, change it, and create a new hash value. However, if an attacker now intercepts the message and the hash value, he won't be able to make any changes, because if he changes the message, he won't be able to create a new valid hash value as he doesn't know the shared secret. The receiver will then receive the message and the hash. He will take the message, combine it again with the same shared key, so the receiver and sender need to share this key in a secure manner, and calculate again the hash value of this combination. If this calculated hash value is the same as the one they received, then the message has not been altered. So this is a way of authenticating a message and making sure that it has not been changed. The second way of providing message authentication functionality is through symmetric encryption. Encrypting the message will provide both confidentiality and authentication using a shared secret key. If we encrypt the message with our shared key K, then transmit this encrypted message. If then the receiver can decrypt the message with the same key and the resulting message is meaningful, so it's not a set of random bits, then we know the message has not been changed, because we know that besides us and the transmitter, no one knows the shared secret key, so no one is able to properly encrypt the message. Let's assume an attacker would change some of the bits in this encrypted message. Well, then the decryption will result in unintelligible output M, and the receiver will be able to detect that something went wrong. This brings us to the third and last type of message authentication function, namely the message authentication code, or MAC. It is an alternative method to provide message authentication. It generates a fixed size cryptographic checksum based on a message and a secret key. It doesn't need to be reversible, in contrast to encryption, which generally makes it more efficient. It works by taking a message M, sending that as input to our MAC, together with the secret key K, and then concatenating the resulting cryptographic checksum to the message M. This is transmitted over the network, and the receiver can check if this checksum is valid in the same way as with hash-based message authentication. Namely, they recalculate using the same key K and the same MAC the cryptographic checksum and compare that to the version that was received. If the comparison is valid, they know the message was not changed. And I have a question for you related to message authentication. Can a message authentication code, or MAC, be used to provide a digital signature? Possible answers are yes, no, or it depends on the situation. Feel free to pause the video while you think about your answer. And let's take a look at the answer. The answer is no, because a digital signature needs to be verifiable by anyone, while a MAC uses only a secret key. For a digital signature to be verifiable, it makes use of public key or asymmetric encryption, which is part of next week's lecture series. As such, a MAC cannot be used to verify the identity of the sender, so it does not fulfill the requirements of a digital signature. Let's take a closer look at the security requirements of message authentication code functions. Given a MAC and an opponent who knows the MAC but does not know the secret key K, the following three requirements should be satisfied. And as you will see, these requirements are very close to those of cryptographic hash functions. First of all, if an opponent observes a message M and its associated message authentication code, it should be infeasible to construct an alternative message M- such that the message authentication code of both messages is the same. Second, given two random chosen messages, M and M', the probability that they have the same MAC should be 2 to the -n power for an n-bit message authentication code. This means that the code should be distributed uniformly at random over the entire output space. Finally, if M' is a node transformation of M, then the probability of them having the same message authentication code should not be larger than the probability of two random messages having the same message authentication codes. This avoids bias in the generation of the code if two messages are similar. To finish this video, I have a couple of questions for you. First, given a MAC with key size k bits and code size n bits, where n is less than k, what is the computational effort needed to brute force the key given a single message code pair? Is it 2 to the k power, 2 to the n power, or it is impossible to unambiguously determine the key? And let's take a look at the correct answer. The correct answer is C. The key cannot be unambiguously determined. This is because since the message code space is smaller than the key space, multiple keys can result in the same message authentication code for the same message M. To get a better understanding of this concept, I have an exercise that you can try on your own at home. So given a key size k of 24 bits and a code size n of 16 bits, how many text code pairs are needed to unambiguously determine the key? Good luck solving the exercise. In the next video, I will talk about some specific implementations of message authentication codes.